Hey. Oh my gosh, tell Mac you got class to get to. I don't blame him. Online school is
Whack.
Wackadoodle dandy.
whack.
Horrible.
Horrible. Wackadoodle dandy. Is that what you said, Maddie? Wackadoodle dandy? Alright. I like wackadoodle dandy. I'm going with that one. Alright, so sorry, messed with my camera for the homework. Alright, so we're gonna go back to that ACT prep class. Remember in our last set of notes, we designed an experiment so that half of the kids who signed up went to a classroom teacher and half went to the online teacher. So we're going to say the results are in from that. The kids who took the online class got an average ACT score of 23.2, and those who took it with the classroom teacher got an average ACT score of 21. So can we conclude that the online ACT prep class caused better scores?
Yeah.
Why?
There was
Because they got better results, okay?
there's a treatment.
There was a treatment imposed. Hannah said no, though. Why did you say no?
Because, like, with the other paper, it was basically like discussion.
What do you mean? The thing with the other paper.
Like, because you have to show how it proves, but it doesn't say how it's proven. Maybe I'm wrong. I don't know.
But you're all kind of right. The answer's maybe. It's just like statistics to not give a solid answer, right? Nate?
Is this like a correlation does not equal causation type of thing?
Yeah, we talked about that last week. So usually experiments, because you have imposed treatment, you can prove causation. Experiments allow cause and effect conclusions. Surveys, samples, observational studies, those don't allow the cause and effect. We can only say there's correlation. The reason why we're not saying that it's caused a better score, and we'll get into this a lot more later in the year, is that we have to prove that the observed effect is so large that it would rarely occur by chance. And so really we have to prove that it's statistically significant. If it's not statistically significant, then we can't really say it was the type of ACT prep class that they were in that caused the better scores.
Does this mean we're about to get back in the numbers?
No,
Oh, we're not going to
Danny.
calculate it?
not yet.
Oh, okay.
I wish we got to. No. Yeah, this is chapter 4. I don't think we start really doing statistically significant until chapter 7. Might be chapter 8. 12.
12?
Yeah.
What are we gonna do?
We need to know the idea right now that just because you have an experiment that has certain results, we still can't say it was caused by the experiment because we aren't testing whether things are statistically significant or not yet. And I mean, this is the definition here. I will have a question for sure, multiple choice, about whether what the definition of statistically significant is. And even though we're not going to get into it and testing it yet, we use alpha equals 0.05. unless the problem states otherwise. But that's the default alpha level for statistically significant, which is saying that these results happen less than 5% of the time. So we can say that it happened because of our experiment, not just by chance. But we'll get into that later. Alpha, it's a Greek letter.
Yeah. What's the name though?
It's our, it's the probability. So if these results happen less than 5% of the time, so this is saying 5% of the time, then we would say it's statistically significant and it happened because of the treatment, the online class or the classroom teacher. If we have a probability higher than 5%, then we say it just happened by chance, so it's not statistically significant.
Mm-hmm. And that's what that star means?
Yeah. I don't know why they chose alpha, but that's the Greek letter they use. Any other questions? So like I said, we're not going to start testing yet, but we need to know that what the definition is, and that until we start testing it, we can't say for sure cause and effect. We can say it might be, and then we'll later in the year learn how to test so that we can say the cause and effect relationship is there. So like I said, today is more about different ways we can design experiments. Last time we looked at the comparative randomized design, randomized comparative design. I always mix up the letter or order of the words. But there's two other designs that you need to know, block design, and then we're going to talk about matched pairs design. So, we're going to keep with the ACT prep class idea. We're going to say the counselors at EKHS hypothesized that the online versus classroom results are being greatly affected by the grade of students that were put into each treatment group. They know that juniors generally score better on the ACT than sophomores. They think that the average ACT score for the online class is much higher because there may have been more juniors in that class than in the classroom teacher prep course. How do we argue against that? Random assignment, if you remember the 4 principles of experimental design, random assignment is one of them. And the reason we do it is so that our groups are roughly similar. So random assignment would be our argument that the groups should be similar. The whole idea behind random assignment is that then we eliminate or reduce the confounding variables. But sometimes people don't believe that random assignment is going to make the groups similar. So then you have other ways that you can get rid of those type of confounding variables, which is using a block design. So we're going to design a new experiment. Same thing as last time, we have 50 students. And to do a block design, we're going to add a step before our random assignment. So the issue here is that the counselors think that the grade level is what caused the ACT scores, so they're juniors and sophomores. So the first thing we're going to do is we're going to break our 50 students by grade, so sophomores and juniors. Just for the sake of making a nice experimental design, I'm going to say we have 30 juniors and 20 sophomores. So that right there, separating them based on their class, that's what is known as the block step of the experimental design. So we broke them into groups based on a shared characteristic. then once they're in their blocks, then we do the random assignment. And then I'm going to take half of my juniors, put them into treatment 1, the other half into treatment 2. Same thing for my sophomores. And I, of course, didn't leave much room for myself. So let's see if I can squeeze this in. We're going to call this group 1, and I'm going to abbreviate. My speaker's making a weird noise, and it's not even on. Sorry. And then group 2. And same thing with the sophomores. We're going to put half into group 1 and half into group 2. So 15 of the juniors go to group 1, 15 to group 2, 10 sophomores to group 1, 10 sophomores to group 2. And since I'm running out of room, I'm going to abbreviate treatment as just T. I'm going to say treatment number 1, which is going to go to the juniors and sophomores who got put in group 1. And we're going to, let's say they're the online kids. So they got the online prep class. And then group 2 gets treatment number 2, which is an actual teacher. And then the other difference here is when we compare at the end, we're going to compare juniors to juniors and sophomores to sophomores. So before we had everybody being compared to one another, but now we're just going to compare juniors with juniors. So we're going to compare scores. Compare. I almost forgot my E on compare. And then same thing, we're going to compare the scores within the block of sophomores. Am I off the screen? Okay, thanks, Trey. Yes, sir.
So the block design is essentially just breaking them into strata?
Yes,
Okay.
but we don't call it strata.
Yeah, why do we give it such a name?
I think to distinguish between a survey and an experiment.
Okay.
So it pretty much is, you broke them into strata. The definition of strata is similar groups that are similar because of a shared characteristic. Same idea when you break them into blocks. But for an experiment, we call it blocks. For a survey or a sample, we call it strata, which I agree is kind of weird, but that's how they do it. So just a couple definitions down below. It says in the previous experimental design, the population was split into 2 groups, juniors and sophomores, which we call blocks. A block is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect the response to the treatments. When the random assignment of experimental units to treatments is carried out separately within each block, we have a randomized block design. When you use a randomized block design, separate conclusions can be made for each block. And then just like Nate pointed out, we don't want to confuse, there we go. We don't want to confuse a randomized block design with a stratified random sample. So when we're doing a survey, we use a stratified random sample. when it's an experiment, it's a randomized block design, but they are very similar.
Why can't they just use it as the same
I don't know. I feel like I've said it before. I feel like sometimes in math we get used to a name and then we change it just to change it, not really for any other reason. Like in chapter 6, instead of calling it the mean, we call it expected value. And it's like, why? It's the same thing. You're finding the mean. But that's what they do in math. Alright, so that was block design. Now we're going to talk about a matched pairs design. Still looking at the ACT prep class. So this time we're going to focus only on the juniors. And counselors are now worried that a student's GPA is certainly going to affect their ACT score, and they want to be sure that the different GPAs are being evenly distributed into the two treatment groups. So what's one way that we can make sure GPAs are evenly distributed? Any ideas? Carter? In theory, random assignment should split them similarly, but the counselors don't believe me on any of this. So what's another way I can, for sure, split the GPAs so that they believe me that they're equally split? No? You guys are going to be like, oh yeah, that makes so much sense. Let's take the list of kids, put them in order by GPA, and then just put the top kid in group 1, the next top kid in group 2, and just alternate.
Every other one.
Every other one.
Oh.
So when you use that method, we've now created a matched pairs design. And really, it's very similar to a block design because essentially what we did is we created blocks of size 2. So we're taking the highest student with the student with the highest GPA and then the next student with the highest GPA, and we put them in different treatments and then we compare their scores. So we've created a block of size 2. More often, when you do a matched pairs design, each pair consists of just one experimental unit that receives 2 treatments. So the most common example here would be a pre-test, post-test, where Hannah would take the pre-test and she'd take the post-test. So I've done both treatments on her, but she's her own pair. So she did both treatments, the pre-test, then the post-test. The order of the treatments can influence the response. So if you're using the same subject for both treatments, you need to randomize the order of the treatments. My other example, and this is gonna age me because I don't think you guys know this. The Pepsi Coke challenge was a thing back like, I want to say I was in college, and they had this commercial. I'm pretty sure Pepsi put out the commercial, and they would have a person try both Pepsi and Coke, but they wouldn't tell them which one was which. And of course, the commercial had it showing that people preferred Pepsi over Coke. But that would be a matched pairs design. Like if I gave Trey 2 little cups, one was Pepsi and one was Coke, and he doesn't know which one is which, and he tastes both, he's getting both treatments, but it was done just to him. That's another example of a matched pairs design. If I were to do it, I would have to, for all of you, I would have to make sure I didn't give you all Pepsi first or all Coke first. I would have to randomize the order in which you tasted them to make it a good experimental design. Any questions there? All right. The other thing you're going to homework is you're going to be given a situation, and you're going to have to talk about to the I can't use words today. That's why we need to go back to numbers. It's called the scope of inference. Really what it is deciding how far you can generalize your results. So what can we conclude in each of the following situations? The first situation, the U.S. Census Bureau carries out a monthly current population survey of about 60,000 households using Table D. Remember, that's your table of random digits. You have to know how to use it because multiple choice questions will give you parts of the table. But when you're designing your experiment or sample, you can use your calculator. So they use Table D to select 60,000 households. They find that 12% of the sample are unemployed. So what is the conclusion that we can make? Because they used Table D, which means they're doing a random sample, we can infer that 12% of the population, the U.S. population, is unemployed. If we didn't have the random sampling, we could not make that conclusion. And I said population before, but I can only infer it to U.S. households because it was a household survey. And then situation 2, scientists performed an experiment that randomly assigned 21,000 volunteer subjects to one of 2 treatments, sleep deprivation for one night or unrestricted sleep. 2 days later, the unrestricted sleep group scored significantly higher on a performance test than the sleep deprived group. So here, we have random assignment. We also have an experiment. So because of the random assignment and a treatment being imposed, we can say that the unrestricted sleep caused the higher scores. I really should learn to give myself more room to write these things. Sorry. So when it comes to making inferences about populations, if the individuals were randomly selected, then we can make inferences about the population. So that would be an observational study. When it comes to inferences about cause and effect, if the individuals were randomly assigned to treatment groups, then we can make inferences about cause and effect relationships. And that would be if it's an experiment, randomly assigned to treatment groups, and up here, random selection. When you're discussing the scope of inference, make sure you always put it into context. So like I did in the above examples, I said U.S. households, and like I even said, I first said population, but then I went back and said, oh, I can only infer to households because it's a household survey. And here I was able to say unrestricted sleep causes higher scores, so you do have to put it into the context of the conclusion that you were given. Any questions? Trying to decide if I want to do this with you guys or not. I think kind of like yes. Maybe here. We'll try it on our own first. I'll give you some time to read through and think about it, and then we'll go over it together. But first, I'm gonna have you try it on your own. out, please, with Lloyd?
Yes.
Thanks. All right, Anna is gonna put the answer to the board. A lot of you are, what? Yeah. I know, even when I was doing it, I missed it until I went, why did I skip A? And then I went back and actually found where I labeled A and read it again. And then I realized it was a question, which is why I typed it that way. But it turned.
Oh, we're supposed to write it down here? Oh, that's good.
All right, thanks, Hannah. So that's a randomized comparative design. We took our 40 students and went straight to random assignment, compared them at the end. So that's your most basic experimental design. Michelle is going to do B for us. How do you fall asleep?
It's not hard.
I
It's
could,
pretty comfortable.
my head would be like falling over.
No, I only sleep good with clothes. I
Wow.
don't sleep good with bed.
Thanks, Nathan. That makes us teachers feel so good. So, so when you come to school, it's because you need to catch up on sleep.
Well, I get good sleep in my bed, but I get great sleep in class.
Bruh.
Thanks.
It's like your voice moves into sleep.
Are you saying I'm monotonous? Like, my tone is that, like,
No.
listening, or, I have to know
That makes me
different.
uncomfortable. I don't like that.
You want to talk to people? No. All right. So Michelle came up with two different ways that, or excuse me, one. Somebody else had two. Was it Haley? Haley, did you have two ways? Yeah. So Michelle came up with blocking by how long they've been driving, because in theory, somebody who's been driving a little longer probably, I'm not endorsing driving and talking on the phone, but probably could do a little better with driving and talking than somebody who's brand new to driving altogether. So she said divide the groups by how long they've been driving. Make group 1 driving 1 to 2 years, group 2 3 to 4 years of driving. Haley, what was your other one?
Well, I think it was like age.
Age, thank you. So you could do it by age. The thing about age, though, is not everybody gets their driver's license at 16 anymore. Some people wait. So age could kind of do the whole driving experience, but it may not, because like I said, not everybody gets their driver's license at 16 anymore. And then why is it so important to randomly assign the treatments within each block? So I saw a lot of you that had something about reducing bias and to make the results as accurate as possible, which are both great valid points, but what is the whole idea behind random assignment, Anna?
Well, wouldn't it be so, well, okay, to get different conclusions for each block, so you have like more, that's not what your question was, but I read the one before you said that, so.
Okay,
I was just saying.
you were adding to
different
this one?
Yeah, you can
Yeah.
get different conclusions.
Yeah, so we could see if the 1 to 2 years, just driving versus driving and talking, has a different result than 3 to 4 years experience driving between the two treatments. What is the point of random assignment, Michelle? I'm sorry, I didn't hear you.
Does it say the better representation population?
No. I mean, maybe. I could roundaboutly get to what you said. So the idea behind random assignment is that our groups are going to be similar. So even though we've already blocked them by driving experience, there's a lot of other variables that could be mixed in to our conclusion, such as gender. No offense, boys, teenage boys, your insurance is higher because statistically speaking, you guys are worse drivers.
Sure.
It's been proven time and time again. I'm not trying to be rude.
No, I refuse. But I don't know, like, basic, like,
Never should have said that.
guys just, like, don't care, but girls just don't know how.
Can I have your insurance?
Yeah.
What do you even mean?
They don't.
All right.
It's so low.
I thought you had to be like 40 to get insurance. That cheap. What do you mean?
I don't know. My insurance is so cheap.
It's not the car you drive.
That's fair.
car.
And
then also
You drive a Mustang.
Yeah, but that's not technically mine.
Driver's ed will reduce insurance
I
costs.
do driver's
Good
ed.
grades reduces insurance costs. Being female reduces insurance costs. Good grades. Only if you submit them to them, but they will reduce it because, I don't know, you're more responsible. You have good grades. I don't know. I don't know that one. Alex,
Have you seen the people that drive here?
have I seen what?
Have you seen the people that drive here?
Yeah.
Yeah. Teenagers.
I'm just saying, it is something that has been proven. Teenage boys have a higher risk of accidents than teenage girls. By doing random assignment, it should roughly create similar groups within the blocks
When's the last time
so that we could say that we've reduced our confounding variables. The whole idea behind random assignment is to create similar groups.
Truth. She's a curve cover? Yeah. I was like, okay, how do you do that?
There's this one old lady that drove through our store. Suck on that statistic.
Someone maybe were ending